In material science, plastic deformation is primarily governed by slip. Under normal conditions, applied stress forces dislocations to glide across crystal planes. But sometimes, the lattice refuses to budge. Dislocation slip has strict thermodynamic and geometric limits. Drop the temperature toward absolute zero, apply strain at ballistic speeds, or force deformation onto rigid structures, and standard slip mechanisms lock up. The required stress to move a dislocation simply becomes too high. This graphic outlines what happens next. When the resolved shear stress on primary slip systems approaches zero, the material must activate alternative deformation modes to accommodate the incoming strain. We see four main pathways: deformation twinning, stress-induced martensitic transformation, macroscopic kinking, and creep. To survive extreme environments and avoid catastrophic brittle failure, engineered materials bypass these frozen slip planes entirely. They rely instead on massive structural buckling, spontaneous phase transformations, and atomic mirroring. These advanced plasticity modes function as mathematically predictable survival mechanisms, enabling engineered materials to endure conditions that would otherwise lead to immediate fracture. We begin with stress-induced martensitic transformation. Instead of gradual atomic gliding, the material generates a massively sheared region to instantly absorb applied energy. Notice the shift from the original austenite surface to the tilted martensite surface, anchored by the central midrib. The bottom labels show a complete phase change. Carbon steels convert from face-centered cubic to a body-centered tetragonal plate, while titanium shifts to hexagonal close-packed. This rapid on-the-fly conversion is called the trip effect, or transformation-induced plasticity. Stable austenite physically transforms into a completely new crystal structure, while the deformation is actively happening. By generating fresh martensite plates during deformation, the material experiences a massive spike in its work hardening rate. This drives up the ultimate tensile strength, allowing the metal to absorb significantly more strain. By changing its phase during a high-stress event, the crystal builds an internal shock absorber to delay necking and fracture. When phase changes aren't an option and slip remains locked, crystals can buckle. Macroscopic kinking is a cooperative second-order buckling mode, operating on a much larger scale than a microscopic dislocation kinking along a single line. We are looking at a kink band region, labeled ABCD, where slip planes abruptly bend and deformation concentrates. Mathematically, the K2 plane defines where slip occurs, while the K1 plane acts as the boundary where deformation behaves as simple shear, trapping strain inside. This specific geometry only forms under a strict deterministic condition. The resolved shear stress on the primary slip system must be nearly zero. The material has absolutely no other geometric option to yield. The direction of the applied load dictates the band's behavior. In case 1, a tension axis perpendicular to the active basal plane causes the kink band to expand. In case 2, applying a compression axis parallel to the kink plane puts the kink surface itself under severe compression. In this way, macroscopic kinking acts as a mandatory geometric pressure release valve. In rigid structures like HCP crystals, when stress builds and normal slip cannot accommodate the strain, the lattice folds to survive. The most vital secondary deformation mechanism after normal slip is mechanical twinning. This grid maps the atomic mechanics of the process. A specific volume of the lattice undergoes a uniform shear, resulting in a coordinated displacement of atoms. Across that diagonal 1-1-2 twin boundary, the blue deformed grid becomes a perfect mirror image of the original undeformed lattice below it. The physical difference between this and normal slip lies in distance. Normal slip moves atoms by full integer multiples of their spacing. Twinning moves atoms by tiny, exact fractions of atomic distances. In this model, atoms in each adjacent layer move an equal fractional distance relative to the layer beneath them. This produces localized shear over a finite thickness, visible by tracking vectors A1 and A2 from their initial positions to their final twinned alignment. Twinning re-architects the crystallographic orientation on the fly. It alters the direction of the lattice without breaking structural continuity. Because this fractional movement is strictly proportional, the resulting shear strain is a precise, calculable geometric magnitude. The equation panel here defines that magnitude. Shear strain, or gamma, is calculated by dividing the shear displacement, S, by the twin width, h. This directly equates to 2 times the cotangent of theta, the angle between the primary and secondary undistorted planes. The availability of these twinning planes is dictated entirely by crystal structure. Face-centered and body-centered cubic metals each have only one specific twinning mode. But looking at the table for hexagonal close-packed metals like titanium and zirconium, we see a complex array of required modes to handle strain. Macroscopically, these twinned regions assume a distinctive lens-shaped morphology. To accommodate this abrupt structural shift, the twin boundaries must be packed with a cumulative arrangement of boundary dislocation arrays, represented by these interlocking symbols along the edge. This specific lens shape, bordered by dense dislocation arrays, is nature's physical method of minimizing overall elastic strain energy in the surrounding matrix. This graph charts the thermodynamic triggers for these mechanisms. Notice the dashed red and blue curves. As temperatures drop or strain rates spike, the critical stress required for normal dislocation slip rises exponentially. Conversely, the twinning threshold remains flat. It is almost entirely temperature insensitive. When the stress required for slip becomes prohibitively high in extreme environments, twinning requires less energy and takes over. In hexagonal close-packed metals, altering the stacking fault energy or the atomic spacing dictates this threshold. Looking at the timeline, once the Co/A ratio exceeds 1.73, basal slip can no longer handle the load alone, and twinning must occur concurrently with deformation. We can physically observe this transition. This stress-strain curve for cadmium shows highly jagged, serrated peaks. These discontinuous flows map the rapid formation of twins, a process so fast it often produces a distinct acoustic emission, historically called the tin cry. Twinning provides a crucial and necessary detour that bypasses crystallographic dead ends, aligning the internal lattice so that standard slip can resume its role as the primary engine of plasticity. This diagnostic matrix isolates the mechanics of the 2 primary engines of plasticity. Normal slip utilizes full atomic integer distances, distributing shear non-uniformly. Twinning requires atoms to move in exact fractions of their spacing, shifting uniformly across all layers. Slip preserves the original crystal orientation as layers glide past one another. Twinning physically alters the crystal orientation, generating a unidirectional mirrored plane. Finally, look at the stress dynamics. In normal slip, the stress to cause initial yielding is lower than the stress to continue flow. Twinning reverses this. The energy required to nucleate a twin is significantly higher than the stress required to move it. That high nucleation threshold followed by a lower flow stress is exactly what causes the violent, jagged drops in the macroscopic tensile curve we saw earlier. The twin bursts into existence, releasing energy, then glides easily. Dislocation slip is the path of least resistance, but by mastering these advanced kinematic reorientations, kinking, twinning, and phase transformations, engineers can predict how materials will behave and survive when that path is blocked.